I'll begin. Oh yeah. Once everybody's, we're missing somebody. Yeah. So, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for the students, this class. Just ask you just bless our work today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, yeah, I was looking at my schedule, and full disclosure, I forgot I needed to work through some stuff in the book so I could present it to you guys, and I haven't. And I don't want to just kind of go off half understanding. I mean, I understand this stuff. I just haven't thought about how I want to say it to you guys, And so for that reason, I'm going to kind of skip ahead a bit, and I'll come back to 3.1 in the textbook. It says I'm covering 3.1, 3.2, 3.3 today, and that's not.
I read that earlier.
That's funny. So.
One time I prepared for class.
One time you're prepared. All right. Well, to recap, last time we learned that if we, so I said some of these things last time, but it was not. I'm not happy with the way I wrote it on the board, so I just wanted to revisit it one more time. So if we had ddt of f composed with, say, phi of t, right, or maybe gamma. So gamma is a path, and f is a complex valued function, right? So gamma is a mapping from some, say, interval, which is a subset of the reals, to the complexes. And we'll also write gamma is like x comma y, or if you like, x plus iy, if we're going to use the complex notation, and we probably will. Then I showed you last time a proof that this could be written as partial f partial z times dz dt plus partial f partial z bar times z bar dt, right? So I looked at the details of that, and we said, okay, so if partial f partial z bar is equal to 0, then we have this wonderful formula that the derivative with respect to time of, say, f of gamma of t is simply equal to df dz at gamma of t times d gamma dt. If I write down the dependence, which I'm omitting, right? You should understand, of course, this chain rule, these things are all evaluated at the path as appropriate with the chain rule. And so my point in all this is if I have a point here, and in the z-plane, let's say, yeah. If I have a point in the z-plane and I have two curves, right? Maybe one like this. All right, so here we've got like gamma 1 subprime of, let's say, t naught, right? And then that maps under some complex function, right, over here to the w plane. So I've got w equal to u plus iv over here. And of course here, this is the z-plane, so we had z is x plus iy, all right? Then the image of the blue curve under the map gamma, f rather, is whatever it is, all right? I'll just draw it like this. And so this point over here would be f of, well, let's say p naught. That point, yeah. And so I'm going to say that this point right here is p naught. All right, so in particular, gamma of t naught is equal to p naught. So I was saying this stuff in words, but I wanted to write it down. So like, this is my path parameterized by gamma 1, and its image over here in the w plane is f composed with gamma 1. Right? So that's one path, and we could do that. And then if I have a second path, right, maybe like this, all right, again, I'll parameterize it so that we can compare nicely. So this is gamma 2 prime of t naught, the tangent vector to path 2, right? Then it gets mapped, to something over here perhaps like this, yeah? And so here's my tangent vector. This is the curve f composed with gamma 2, and the tangent vector here and there. So I haven't written the formulas for the tangent vectors in the W plane yet, but I will here in just a second. So, whoop, yowzers. So F is the mapping that goes from here to here, right? And so these guys, we'd have like gamma, my bad, a more brief notation than this would be, this I could rewrite as like F composed with gamma prime of t, right? So here I have the tangent vector F composed with gamma 1 parentheses prime of t naught. And down here I have the tangent vector F composed with gamma 2 parentheses prime of t naught, right? And what I was trying to argue to you guys last time is that the angle between the initial paths here, right, has to be equal to the angle between these paths over here if we're dealing with a holomorphic map, right? If we're dealing with a complex differentiable map, but there's a little bit more fine print, right? See, because I have what? I have like F composed with gamma 1 prime of t naught is equal to what? It's equal to F prime of p naught times gamma 1 prime of t naught. And I also have F composed with gamma 2 prime at time naught is equal to F prime of p naught times gamma 2 prime of t naught, right? And as long as you know, as long as we know that the derivative at p naught is not equal to 0, then we've studied how complex number multiplication works already, right? If you multiply a complex number by another complex number, what it does is it rotates it by the angle of the number and it rescales, right? By the magnitude of the number. So like if F prime of p naught was, you know, say equals to, I don't know, R naught e to the I, say theta, say theta, let me not use theta, let me say beta for the sake of discussion. Then what would happen is both of the tangent vectors, the blue one and the red one, they're both rotated by an angle beta, which maintains the difference in the angles between them, right? And so this conservation of the angle of intersection between curves, if a map has this property, it's said to be conformal. So this is so-called conformality. And you can talk about, so it's a conformal map, you know, provided F prime of the point is not equal to 0. So you read all about the roots and the repeated roots and the factorization and all that? Yeah, I'm so sorry. I will come back to that. We will cover that. And maybe you can do the homework on it, nobody else can. Then you could sell your answer to Daniel, because he's not even in this class yet, you know? But okay, anyway, I just wanted to actually write this all out because I kind of had it all crammed into a little part of the board right here last time, and I don't like that. Now I have more details in the notes. Like I actually work out the angle between the vectors in terms of like the inverse cosine of the quotient as appropriate, and everything. So that's one thing. I just wanted to revisit the conformality, and like I said, I think that's one of the main answers to like what's the geometry of a complex map. Well, if the derivative of the complex map is non-zero, it does preserve the angles between paths that it transforms. All right, so what's up next? So I was supposed to cover, like I was just saying, section 3.1, 3.2, 3.3. I think actually I've already covered large chunks of like 3.2 and 3.3. So it's just 3.1 I'm kind of nervous to do today. So sorry. Tell you what, if I cover everything else, I'll circle back to it. I'll do it today. I'll try, you know. Let's see here. So 3.2, we have exponential, trigonometric, and hyperbolic functions. So, you know, he defines the complex exponential. We've already done that. Theorem 3, e to the z equals to 1 if and only if z is equal to 2 pi ki, where k is an integer. We've done that already. Two complex exponentials are equal if and only if their their inputs differ by an integer multiple of 2 pi. We've talked about that. The definition of sine z, definition of cosine z, proof that sine z is equal to 0, we've done all that. Definition of constant. Goodness gracious, I've already covered section 3.2 in its entirety in here. So, then the logarithmic function, section 3.3, he defines the little log and the big log and looks at their properties. So, I guess it would be good to mention that, well, let's just define it again, right? So, what's the capital log of z is equal to what? It's equal to the natural log of the modulus of z, right? Plus I times arg of z. And this is for what? For z not equal to 0, right? And what was arg z equal to? It's equal to theta, right? Such that z is equal to modulus of z e to the I theta, and what? Theta is an element of what?
Oh, negative pi to pi.
Uh-huh. Yeah, negative pi to pi, minus pi not included, pi included, right? So this was the argument. Right, so we defined that. We looked at these before. We've done a fair amount of calculation with these at this point. And what was little log? What was the difference? So what did we do? We just did big log, right? Actually, before I get to that, we had little arg, right? Which is just what? It's theta such that z is equal to the modulus of z e to the I theta for theta in the reals, right? It's all possible standard angles that represent the number. Now, of course, both of the args have to be for z not equal to 0, right? And by properties of the complex exponential or trigonometry, whatever you like, you could say that this is arg, big arg of z, plus what? Plus like 2 pi z, right? Because you're just adding integer multiples of 2 pi. Now, little log is what? Little log of z is equal to, oh man, I am my own worst cameraman. I tell you what, let's see here. It's okay, you guys are all here, so no harm, no foul. So little log, you could say it's just big log, right? Plus 2 pi iz, right? I suppose alternatively you could also say it's the natural log of the modulus of z plus I little arg z. That would also be true. Yeah.
Why is it little arg and not big arg?
They're different. If what?
Well,
I'm sorry, I didn't finish your sentence. I'm sorry.
Big log of z is natural log of the modulus of z plus I big arg of z. So if you plugged in that equation to there, wouldn't it be the natural log of the modulus?
That equation, where are we talking?
If you
Are we talking about here?
Yes. Wouldn't it be big arg? Right? Because you plugged in both that.
Well, yeah, I mean, this is explicitly natural log the modulus of z plus I times big arg of z, and then
Okay.
and then you see what happens here is I can factor the I out, and I get big arg plus 2 pi z. So my point is that these things are interrelated, right? And really, the real issue is the argument, right? Like that's the whole thing. Is like your choice of angle is where all the funny business happens, right? So you guys had a homework problem that I think most of you have worked, I hope. And what you proved is that if we look at the slit complex plane, right? So here's 0. And if we look at, coming from this way, and if we look at coming from that way, on the one hand, we get arg of z going to pi up here, right? And down here, we get arg of z going to minus pi at a particular point here, for z equals to, x less than 0, right? So as you approach any point on the negative real axis, from the top we're at angle pi, right? And it's equal to pi, everything until you actually get to the ray. So the limit will be equal to pi, because when we take a limit, we consider points close to, but not at the limiting point, right? So it's pi from above, it's minus pi from below. That means that the limit of the argument function does not exist on the negative real axis. So in short, argument, arg, is discontinuous, on, let's see here, z, well, I don't know, what's the right notation for it for you guys in here? We could say z equal to x plus iy. How about just I say, let me be weird. X plus iy, this is a really dumb way to say it, but x is less than 0 and y is equal to 0. There you go. And of course I could throw in equal 0 here, right? I mean, maybe that's not, now we're going to get into some sort of minutia, because can you talk about discontinuity of a function where it's not defined? Well, you definitely can in pre-calculus. We do that all the time, right? But if you think about calculus, we really only give a careful definition for where a function is discontinuous if it's a point that's either in its domain. I don't know. So here we can get fussy, but I'm going to shut up because it's not a particularly interesting question that I'm raising. Anyway, so my point is arg is discontinuous. And one of the theorems that you proved in last homework was what? If f prime of z naught exists, right, then f is what? It is continuous at z naught, right? So what does this mean about the argument function? It definitely can't be part of a complex function that is going to be continuous on the whole complex plane, right? There's a discontinuity for the argument on the negative real axis. So if we want to talk about the log, or things built from the log that are complex differentiable, right? Well, forget about complex differentiable. If we want to talk about something that's continuous, we can't include this negative real axis if we're using the arg to formulate something. Right? So while the logarithm is defined for all non-zero complex numbers, we can't get that it's differentiable, complex differentiable for all non-zero complex numbers, because it can't be complex differentiable on the negative real axis, because if it was, that would imply it's continuous, but it's not. So what we can say is this: log is, if you log z, you could say, so here, all right, fine. Here here's an abuse. You guys tell me. Should I write log z is an element of the holomorphic functions on the slit complex plane, or should I say that log is an element of the holomorphic functions on the slit complex plane? So this c minus is the complex plane with the real negative axis deleted, okay? I don't want to take points off in here if you say one versus the other, all right? So, but admittedly, this is an abuse of notation, right? Log, I would say properly, is a good notation for a function. This is the value of the function at z. It's like when we say f, is f a function or is f of x a function? See, but f of x is actually the value of the function at x. But you've been taught f of x is a function, right? And I don't want to quibble with you over that in here either, right? There are people who care a lot about this, but I'm not one of them. I do want you to understand there's a distinction, right? How do you define f? You define f by what happens when you plug in x, right? Or z here. Okay, so what is the derivative of the log, though, here? So how do we figure that out? Well, see what we have is we have that e, well, let's say this. We have, if we let log of z equals to w. So right now, let's calculate what's the derivative of the log, all right? So log of z is equal to w. How can I change this to something I know already know how to differentiate? What do I do? Put it in terms of e? Right, so it's exponentiate both sides, right? So e to the log of z is equal to e to the w. But by design, e to the log of z is just z. We defined log so that that would happen. So we have z is equal e to the w. Right? And then differentiate implicitly, right? So we'll differentiate with respect to z. What do we get? We get dz dz is equal to the derivative of e to the w, but that's e to the w times dw dz, right? Lo and behold, dw dz is equal to 1 over e to the w. But what is e to the w? E to the negative w is true, but put it in terms of z. What is it? It's what? I think you might. It's 1 over z, right? So lo and behold, hooray, we've proved. Prove might be too strong a term. We have derived that the derivative of log z is equal to 1 over z. Now, admittedly, I used something here. I used well, perhaps the implicit function theorem. I used that, or maybe I suppose I used the inverse function theorem here, right? And I tried to give you guys a sketch of a proof of the inverse function theorem last time, right? That if a function has an inverse, so first of all, if you have a complex differentiable function and it has an inverse function, then that inverse function is also complex differentiable. So once you know that, you can differentiate the formulas which define it, like is this formula right here. And we can derive this. So I have a slightly better proof of the inverse function theorem in the notes that rests on like advanced calculus, but I don't test on advanced calculus here, except the linear algebra part that I spent a lot of time in class, yeah.
So both notations are okay with log of z and log?
Oh yeah,
Okay.
yeah, either would be fine. So there you go. This is how we differentiate log, all right? This is not surprising, right? And remember we defined log sub alpha of z is equal to, what was it? Natural log the modulus of z plus I arg sub alpha of z. And if you'll allow me, you could put a plus or minus up here. You could put a plus or minus here. I think I only put a plus on one and a minus on the other. But that notation is just notation I used to either include or exclude either the upper or the lower limit of the range of the angle. So these are all just notations for saying I'm going to pick a particular like a particular set of 2 pi angles, and either I'm deleting the upper or the lower endpoint. And I think my notation is such that alpha is always included. All right. But anyway, you can go back in the notes and look that up. It just concerns a particular choice of angle. So, but it is also true that e to the log sub alpha plus or minus z is, well, it's z again, right? Like, again, by design, it's just a different choice of standard angle. And so if we set w equal to log sub alpha, either the plus or the minus choice, we'll again be able to derive the ddz of any other branch. So these are other branches, so-called branches of the logarithm, guys. So the principal logarithm is one branch, one choice of logarithm. These are other choices based on making other choices for your angle. But they all do that. So if you want to be sloppy, right, And if you want some sort of like overarching notation that kind of globs all these things together and really has inattention to the detail of the branch cut, you could just write this. d dz of little log of z is equal to 1 over z. And that would be true. But it should be understood that the little log is a multiply valued function. The log sub alpha plus or minus, these are particular branches of that function, right? But they're all united in they're all united in the fact that the derivative of those things is 1 over z. So hooray. Anyway, so all right, let's circle back here. Let's go back down memory lane here. Definition. You guys remember we defined the nth root of z. What was that equal to? It was equal to, as I recall, the ordinary nth root of the modulus of z times the exponential of I times arg of z over n, right? That was our nth root. You can prove that this is actually equal to the exponential of 1 over n times the log of z. So here's a claim. It'd probably be good for you guys if I work that out. Let's work that out. How are we going to work it out? What do we do? I say we start over here and try to get back to here. All right? That seems like a more hopeful path than the other way. So what is the log? It's what?
Natural log of z
Mm-hmm.
plus I of capital R z
Okay. Great.
plus no. Right?
Yeah, no, plus nothing.
Yeah.
So it's the principal logarithm.
Yep.
So laws of exponents. This gives us the exponential of 1 over n. Well, by the way, we can
You can
bring
put that over and
yeah, natural log of value of z to the 1 over n power, but we don't write that in here, so we have to write the nth root of the modulus of z like that. Because this is a real number, and if I take the nth root of a real number, that's my notation in here. I only use the fractional power for the set of nth roots. That is my dogma. It's a convention. I need to make a logical distinction between something to the half power and the square root. Square root's a specific thing. Something to the half power here is a set of two things, plus and minus the square root. And it's even worse here if n is like 7. This is either a particular 7th positive root of a number, or it's the set of 7 roots that are related by multiplications by the 7th roots of unity. Oh. Now, so that's it for that. And then we've got exponential of I arg z.
are you supposed to carry over the 1 over n because it distributes over the right?
No. No. Not anymore. You don't believe me? Good. All right. Just testing. So, yes. That's good. You need to stand up for yourself. We know something's right. You got to stick to it. So yes, that I just forgot to distribute. My bad. Or maybe I did it on purpose for a teaching moment. It was a moment, right?
Yeah.
I achieved it was a moment.
It scared me. I was like, no, I think that's how you do algebra.
Very good.
I know. Mistakes on purpose. But then they would backfire.
I do. It is on my long-term list of things to do for the channel is to like make a college algebra class that only has wrong steps.
Stop.
It's just like all the most popular wrong steps, and it all comes to right answers too, right? Like that's part of it. It has to come to a right answer.
That's great.
Because if you have wrong steps that come to a right answer, it makes people doubt themselves more. So if you want to sow doubt, like the ultimate way is do that. But I think we're done. See, because this is the formula for this is our previous definition, right, of the nth root function. Yeah? Woohoo! Now, why did I do this? Why do we care? Okay, so like, which one of these do you want to differentiate? If you want to figure out what's the derivative of the nth root function, do you want to differentiate our previous definition of it? I don't even know where to start. It would be horrible, right? Like find the u and the v, show that the Cauchy-Riemann equations hold. It's quite horrible, at least on the surface of things. Or, do you want to differentiate this? That's nice. We can differentiate that. Let's do it. So the derivative with respect to z of the nth root of z is what? It is d dz of e to the 1 over n log z. I'll write it that way this time. Which then by the chain rule is e to the 1 over n log z times the derivative with respect to z of 1 over n log z. But that is equal to, well, e to the 1 over n log z times, well, 1 over n z. Something wrong?
No, I'm just like missing something. Why did you start off with like the derivative of c to the nth root equals? So you're saying that the z root n is equal to e to the 1 over n log?
I am saying that, yes.
Oh, right, it is. No.
Right, yeah, we just, yes, yeah.
I keep looking at the top of it
It's,
and seeing.
yeah, I know. I use this because it's, yeah, okay.
Right. That's way easier than.
I mean, we could start trying to find the real, and I mean, I don't know, like, how would you, in any of the viewpoints I gave you guys, the Vertinger, the limit definition, the Cauchy-Riemann equations, find the u and the v, show they sat, I mean, all of those viewpoints, this is quite horrible if you just try to do it directly. Right? Okay, so anyway, now this is not a nice answer yet, but let me show you something, a little trick we can do. We can rewrite 1 over z as, so I've got my e to the 1 over n log z, and I'll bring the 1 over n out front because we want it out there. And 1 over z I can rewrite as,
Wait,
yep.
wait, it's almost there. No, you can write it.
Okay, so I can write z as e to the, well, how about log z? Because that's an identity.
Yeah.
And then this is 1 over n, e to the 1 over n log z minus log z.
And then,
And then what? Yeah?
factor it out.
Yeah, factor. So that's that. That's what? 1 over n e to the 1 over n.
No. You just.
Well, let me leave this for a second. I mean, this is right, I think. But you guys tell me, what do we hope is true? What do you want the derivative of the 1 over the 1 over nth power to be? We should expect what? Like calculus 1, right? We should expect that this is 1 over n, and then like z to the 1 over n minus 1 power, whatever that is. What would 1 over n minus 1 be? I mean, that is what I have here, though.
Yeah. Just factor it out.
Right. So this is the 1 over n. Well, see, the obnoxious thing is I've only given myself a notation for nth roots, right? So I have to somehow rewrite this as an nth root. Oh, 1 over n minus 1 is equal to 1 over n times 1 minus n, right?
Okay.
So I guess I can write this as e to the, I'm sorry, I'm working too hard for this. E to the 1 over n
It's just algebra.
log z, de Moivre's theorem, to the 1 minus n power. So, yeah, 1 over n, nth root of z to the 1 minus n power. Since I'm not allowing myself to write fractional powers. Now, maybe you'd like to live in a world where you could write fractional powers, right? So then, if we're going to do that, if I'm going to suspend my, dogma over not writing stuff to the 1/2, then we need to address the issue of not using all the second roots, right? Like, we need to say something like taking a branch of the second roots. So here, I could write something like, what I'm trying to say is it would not be crazy to write that this is, 1 over n z to the, 1 over n minus 1, and then I would write in parentheses taking principal branch. See, there's an issue with complex powers. Complex powers are sets of things generally. Now, I mean, you're like, well, that's not a complex power. It's 1 over n minus 1. And you're probably right there, right? So maybe there's no danger in this particular example because 1 over n minus 1 is, after all, just a number. But all right, so let me continue down this path, but do something that will be probably easier to follow. How do we define the pth power of z? What is z to the power p? How do you define it? You guys define for me z to the power p. P could be complex. How about this? I do e to the p log z. That is a definition I made before, yeah. Although I think before what I might have done is this is really one branch of z to the p equal to e to the p log z, you see? Because if p is a complex number, there's no reason that the different values in the little logarithm give you the same thing. For example, in my notes, I talk about I to the I, right? I to the I is, e to the I times the log of I. Well, what's the log of I? So we got natural log of the modulus of I plus I times, little arg of I. What is arg of I? Well, I has angle pi over 2, right? So this is literally the set. natural log of 1 is 0, so that's gone. So we get I times I is minus 1, so we get like minus parentheses pi over 2 plus 2 pi j, such that j is an integer. See, that's an infinite set of values, right? It's actually got two tails, if you think about it. For j negative, it becomes increasingly large in this particular problem. For j positive, it becomes increasingly small towards 0. They're all on the positive real axis. So like if I was to graph I to the I, it looks something like, I don't know, if I put in 0, I get e to the minus pi over 2, whatever that is, I don't know.
It's like 0.2 something.
We'll say it's here, yeah. So e to the minus pi over 2. So that's j equals to 0, right? And then if you were to graph j equals to 1, that's over here. And if you were to graph j less than 0, you get minus a minus is a plus, so that makes an exponential of a large thing, so it just gets doop, 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 out further and further. They're more and more spread out, right? I don't know, just whatever. The point is that they're all along the positive real axis. This is what I to the I is. It's a set of values. So if I'm going to talk about a function and how to differentiate it, I don't want to have all the values, right? I want to choose a particular choice, a particular branch. And so what I do is I just, instead of using little log, I use big log. So this is a particular branch of the multiply valued z to the p function, which is not really a function, right? Because you have infinitely many outputs, it's not single valued, right? Far from it. So once we've made this choice, this is a particular complex function that we can study. What's its derivative? If there's any justice, what's the derivative here have to be? Z p to the c minus 1. So you don't even need to take this course. You already know complex analysis. That's good, right? Let's derive it. So d dz of z to the p. So we got ourselves d dz of e to the p log z. And okay, great. So that gives me, by the chain rule, e to the p log z. That was supposed to be a p. P log z times the derivative with respect to z of the inside function, which here is p log z, but we know the derivative of log is 1 over z, right? So this gives me p over z, e to the p log z. And then what can I do?
E to the p log z is z to the p.
Well, that is true, but that will not be, that'll be counterproductive to our larger goal at the moment. I need to convert this to an x. I'm going to do the same trick I just did over in the other calculation, which is that is e to the minus log z, right? Agree? I can change the 1 over z to an e to the minus log z, and then put these together. I've got p e to the p minus 1 log z, and then I'll take you up on your offer to convert it back to a z to a power. We've got p z to the p minus 1. Hooray! Notice this is true for any branch of the power p function. It is not wrong, in fact, to say that, you know, well, here I can just write it this way: d dz of like e to the p log sub alpha plus or minus z, right? If this is, let's say that that's z to the p, I'll put a sub alpha on it with a plus or minus here just to be knowing. Well, that's also going to be p z sub alpha plus or minus function to the p minus 1. I don't have a good notation for it. Nobody does, but all of this still goes through if we choose a different angle function. The thing is, z to the power p, what's the domain? What's the domain of z to the p? If I want z to the p to be an element of holomorphic functions on some domain, well, the domain is the slit complex plane. See? On the other hand, my z sub alpha plus or minus thing to the p would be an element of the... So that is my notation, I think. I hope. I gotta look at my notes, but I probably did that. If I take out the alpha ray, the ray at angle alpha. So this guy is built with the arg sub alpha plus or minus, which has a discontinuity at angle alpha. It jumps from alpha to alpha plus or minus 2 pi at that juncture. It's discontinuous here. So any of these functions, they'll be differentiable on everything except for that jump, because they're discontinuous there, so they can't be differentiable there. Does this make sense? I mean, I know you guys are like, I'm not sure what you meant by arg sub alpha plus or minus. I don't remember how you define that. That's fine. I'd have to look it up too to remind myself the precise meaning of the notation, because I haven't used it this week yet. So I've forgotten. I remember the capital arg. That I remember. That is ingrained. But so there's that. So yeah. So that brings me, I mean, there's one or two other things I should work out for you guys in terms of like inverse function business. Like, is there an inverse sign for for complex numbers? Like, what does it mean, like the arc sign over the complex numbers, or arc cosine? Can we talk about inverse functions of sine, cosine, you know? Well, we can, but, well, even in the real case, how many choices do you have to make an inverse for sine? You're like, well, my calculator only has one, right? But that is an ad hoc choice, right? To restrict sine to, like, you know, minus 90, plus or minus 90 degrees, right? Or likewise for tangent, like the inverse to tangent is, it is, you know, a ad hoc choice of the math community to make it the local inverse for tangent restricted to minus pi over 2 to pi over 2, and for cosine from 0 to pi, right? Well, in the inverse, in the hyperbolic, listen to me, in the complex case, there's also like many choices for how you invert them. And it's a little bit more involved because, you know, you got complex things to think about. But I'm going to save that for another day. I think I want to talk about something a little bit more straight down the center for us. And I still need to come back to section 3.1, admittedly. Sorry. But one of the major calculations in this listen to me, in this course is to find the harmonic conjugate. And so I want to talk to you guys about like the theory of harmonic conjugates. And Laplace's equation. So we'll start with Laplace's equation because that's kind of everything here. So this is a definition. If you have a function phi, right? You know, this is a function, say from the plane, let's say, to R, all right? And phi xx plus phi yy is equal to 0, then phi is harmonic. And I probably shouldn't say R2. I should probably leave myself some wiggle room here. Say like U a subset of R2, all right? Harmonic on U. Sorry, guys. So a harmonic function is simply one that satisfies Laplace's equation. So this notation here is just shorthand for the more monstrous looking partial phi squared, partial x squared, plus partial phi squared, partial squared phi, partial y squared equal to 0, right? Which you could write more compactly as nabla squared phi equals to 0. Indeed, the notation that's above, you could also write in 3 or 4 or however many dimensions you like. The notion of a Laplacian is not just two-dimensional. So this is a harmonic function. So what does that have to do with complex differentiable functions, right? So here's a theorem. If f is holomorphic on a domain D, and f is equal to u plus iv, then u and v are harmonic on D. So let's work it out. What's the proof? So the proof goes like this. So f equals to u plus iv solves the CR equations, right? The Cauchy-Riemann equations. And so what's that mean? That means that ux is equal to vy, and uy is minus vx. So then what? Let us look at D is a domain, which is an open connected set. An open connected set. Could be a disk, but not a closed disk apparently because it's open connected. But anyway, so what is uxx? Well, uxx is equal to ux, the x derivative of that, but that is equal to apparently vy, the x derivative of that. But partial derivatives commute. So I could rewrite this as vx, the y derivative of that, because partial derivatives commute, right? I can do x then y, or I can do y then x. But what is vx? Well, vx is minus uy, which is, of course, minus uyy. So therefore, uxx plus uyy is equal to 0. Thus, u is harmonic on D, because the Cauchy-Riemann equations have to hold on all of the domain. A very similar calculation can be done for v, right? So if we start with vxx, what do we get? So we have vxx is vx, the x derivative of that. And I can trade my vx for a minus uy. Pull the minus out and flip the derivatives, because partial derivatives commute. And then I trade my ux for a vy. Therefore, vxx plus vyy is equal to 0. So if you're looking for solutions to Laplace's equation, in other words, harmonic functions, look no further than the real and imaginary components of a complex differentiable function. It's very nice. We could also define harmonic for like a complex valued function. How would that be defined? So if I had like psi from, say, u, a subset of, let's say the plane for the sake of specificity here. But you could put c there if you wanted. Fine, I'll put c. Complex valued and is harmonic on u if psi xx plus psi yy is equal to 0. And we can easily show that a complex function is harmonic. I'll show you that. So if I start with like a complex function f, right? And I take the xx derivative of it, I'll rewrite that as partial x of partial f partial x, right? But what were the Cauchy-Riemann equations? If we write them for the function rather than the components, remember, it was minus I partial f partial y, which gives me minus I partial squared f partial x partial y. Commute your derivatives. And use the Cauchy-Riemann equation again. Which is I squared partial squared f partial y squared, right? Which is minus fyy. Therefore, fxx plus fyy is equal to 0. In this sense, every complex differentiable function is harmonic. Understand that that means that the real and imaginary components of that function are themselves harmonic. Which is super nice because like solving Laplace's equation is really, really important to science, engineering, and mathematics. So like, cool. It's very neat. Now, we'll talk more about this another day. See, I've only answered one direction. There's an obvious kind of question, right? Which is, what if you try to go the other way? What if I give you a pair? What if I give you a pair of harmonic functions, right? Like, can I go the other way? Is it enough? Is every harmonic function coming from a complex differentiable function? Like, is there like a converse to this idea? How's that go? You know? So I won't completely answer that question today. We're just going to look at some examples here. I mean, if I completely answer that today, my apologies. I don't think it's going to happen. Let's try this out. So a harmonic conjugate. Here's the deal. Definition. If U is harmonic on a domain D, which is some subset of this, say the complex plane, then V is a harmonic conjugate of U if U plus IV is a holomorphic function on D. So a harmonic conjugate is a function that, when you put it together with the harmonic function you're given, you get a complex differentiable function. So let's see if we can work some of these out, yeah? Let's see if we can find the harmonic conjugate for a given function. Okay? So like example 2, I guess. Did I ever go? Well, I don't know. These derivations are sort of like examples, but I guess this is technically example 1, isn't it?
Yeah.
I do feel like that I to the I thing was an example. Is it still on the board? All right, I'm claiming that's example 1. There we go. Ha! What's that?
You had a lot of examples.
Oh, rats. Well, how many? Well, I give up. So how about this? You